Swayam Prabha. Digital India. Educated India.
Welcome to the fifth lecture on static analysis for induced strain actuation. In the last lecture, we talked about the block force method and saw a few cases. Today, we will see few more cases and analyze them using the block force method. So, this case says that there is a beam and this beam has one piezoelectric patch and it is at one side. So, this is a type of asymmetric actuation. Now, in this case, if the beam experiences actuation force like this here, suppose it is F, the piezo patch experiences opposite force F. So, if we look at the beam section, at the mid of the beam section here, maybe at the middle of it, we see that it is under an actuation force F and a bending moment M. So, if the difference from the mid part to the bottom part of the beam is Tb by 2, given the fact that our beam thickness is Tb, then bending moment can be written as F multiplied by Tb by 2. Now, here there is bending moment accompanied by axial force. So, if in this section, if we draw the stress diagram, it will have a linearly varying stress which can be represented as this, as well as due to the force F, it will have a constant stress which can be represented as this. So, at the middle part of the beam, although the bending stress is 0, there will be a axial stress due to this force F. So, from the total stress, which is a combination of this and this, if I subtract this stress, then I can get my bending stress, which is shown here. So, this is the total stress and this is the axial stress due to the axial force F. Now, this epsilon b 0, which is the axial stress due to this axial force F, is constant over the thickness. So, if I subtract this, I get my bending stress. Now, bending stress in terms of bending moment is minus mz by Ib, which we have seen before. Now, from here, if we want to get the strain, we just divide this entire equation by the elastic modulus of the beam. So, this gives me the total strain at the neutral axis, and I subtract the strain due to the axial force F, and that gives me the bending strain part. Now, if I want to find out the strain at the top surface of the beam, which is here in this zone, then I just replace Z by Tb by 2, and then we can get it, and similarly if I want to get it at the bottom surface, then I replace Z by minus Tb by 2 and we can get the strain here. So, the bottom strain as can be seen is this. So, after replacing Z by minus Tb by 2, we get this expression, and here minus S denotes the bottom surface. So, this is my strain at the bottom surface. And the mid plane strain is, mid plane strain means this strain, and that is constant over our thickness, and that is the strain due to this axial force F, and we know that the stress due to the axial force F is this F divided by the cross sectional area of the beam, and then if I divide that further by the elastic modulus of the beam, that gives me the mid plane strain, which is this. Now, in this all these equations we have these terms. So, EAB is the extensional stiffness of the beam, which is EB BB by TB, and extensional stiffness of the actuator, which is EAC 1 means of actuator 1. Now, here we have only one actuator. So, EAC 1 and EAC are same, and that is EC BC multiplied by TC. So, these BC TC they are all they carry the same meaning as they have been carrying. BB means width of the beam, TB means thickness of the beam, and BC means width of the actuator, and TC means thickness of the actuator. And similarly, we can find out the bending stiffness EIB, which is this, and this expression EB BB TB cube by 12, it can be written in terms of EB AB as this also, and finally, we get EIB in terms of EAB as this. So, EIB is equal to EAB multiplied by TB square by 12. Similarly, bending stiffness of the actuator, it has two component. One is the bending stiffness of the actuator with respect to its own centroid, and then another is area multiplied by the distance of the centroid of the actuator from the centroid of the beam, and square of that. So, it is just shifted by the parallel axis theorem. So, this is our EIC 1, and the same after making some approximations that because thickness of the actuator is small as compared to the thickness of the beam. So, ignoring the higher order terms of TC, we get this expression, and finally, EIC is written in terms of EAC as this. Now, at the bottom surface of the beam, we have already seen our expression for the strain. So, we know that this is our this is our strain at the bottom surface of the beam minus epsilon B 0 is this, epsilon B 0 we have got it here. Then finally, combining these two, we can get strain as at the bottom surface of the beam as this. We have just written the epsilon B 0 in terms of the actuation force F, and again the bending moment can be written in terms of the actuation force F as m is equal to F into TB by 2, and after doing all these substitutions, this entire expression can be written as 4 F by EAB. So, the strain at the bottom surface of the beam has been represented in terms of the actuation force F. Now, from here we can find out the extension of the bottom surface of the beam, which is in contact with the actuator, and that is nothing but this strain multiplied by LC. LC is the length of the actuator. So, if we go back, this is the length of the actuator, and we have found out the strain in this region. So, in this region, if we assume that the strain is constant, then if we multiply the strain with this actuator length, that gives me how much elongation our beam surface has experienced at this level. So, which is this. So, we have this strain here multiplied by LC, and that is extension of the bottom surface of the beam. Now, for compatibility, that must be equal to the extension of the actuator. Now, extension of the actuator is this. If the actuator is experiencing a force F, so our actuator, as we drew before, is experiencing a force F here, and if we say that the epsilon P is the free strain of the actuator, then this becomes the expression for the change in length of the actuator, the extension in the actuator. Now, for compatibility, this and this should be same. So, once we equate these two, we get this expression. In this entire expression, the only unknown is F. So, we can take it at one side and solve for F, and we get this expression. So, here we have got the actuation force F in terms of the free strain and the sectional properties EAB, EAC, EAC1, and then epsilon p can be written in terms of the block force. So, this expression can be written in terms of the block force as this, and again we have seen that EAB and EAC1 can also be related to the EIB and EIC1. So, the same thing can be written as this also. Now, so that gives us the expression for our actuation force. Once we know the actuation force, our problem is solved, then we can analyze the beam and find out its deformation and find out other quantities of our interest. Now, if we know the actuation force, we know that bending moment is equal to F multiplied by TB by 2, and then if we put it here, and again we have the expression for the block force, which is MBL is equal to FBL into TB by 2, and after all these substitutions we can find out the bending moment also in terms of the block bending moment. So, actually we need both F and M, and we have got those. So, using both of these quantities we can find out whatever we need in the beam, its deformation, its stress, strain, and so on. Now, we will look into another case where we have the symmetric configuration, but the actuation is not symmetric. So, the top and bottom piezos are actuated with different voltages. So, here the actuation voltage is V top and here it is V bottom. Now, as we did before, we will use a similar approach. So, we will decouple this problem into a bending problem and a extension problem. So, let us assume that the extensional part of the voltage distribution is V1. So, it is V1 and V1 here, and the bending part of the voltage distribution is V2 and minus V2. So, we can say that V1 plus V2 is equal to V bottom and V1 minus V2 is equal to V top, which we can see here. And then once we solve these two equations, we get our expression for V1, the extensional part of the actuation, and V2, the bending part of the actuation, as this in terms of the actuation voltages. So, our problem has now been decoupled into an extension problem and a bending problem. So, from whatever we did on the symmetric and antisymmetric actuations, I mean the axial and bending actuations, we can say that the actuation force due to V1, the extensional or axial force, is ABL1 multiplied by EAB by EAC plus EAB. So, it is an axial actuation, and similar where FBL1 is the block force due to the voltage V, and that is this. And similarly, for voltage V2, which is a bending actuation, the force is FB is equal to this, which is equal to this in terms of the block force FBL2, and the corresponding bending moment is M is equal to MBL2 into this. So, where the block force corresponding to V is this, and similarly the MBL2, the block bending moment, would be FBL2 multiplied by TB by 2. Now, that we know FE and FB, we can say that at the top surface the actuation force is FE minus FB, and at the bottom surface the actuation force is FE plus FB. Now, we will look into one more case, two more cases. Again, these are asymmetric actuations, and here the asymmetric is in the piezoelectric properties. In the first case, the asymmetry is in the geometric property of the piezoelectric patches. So, here the thickness at the top and the bottom piezos are different. So, we can call this as TC top, and we can call this thickness as TC bottom. Thickness of the beam remains same as we have been denoting by TB. Now, here we are actuating them using the same voltage V. Now, as we have seen, even though the voltage is same, but because the thickness are different, so the actuation force can be different. So, if the actuation force at the bottom is say F bottom, and at the top is say F top. Now, again we will decouple them into an axial actuation and a bending actuation. So, let us say that we have an axial part of the actuation which we can call as F e, and that force should be same F e and F e, and similarly we have a bending part of the actuation and that is going to be different. So, again we have F b here and opposite force F b here. So, we can say that F b plus F e is equal to the F bottom and F e minus F b is equal to the F top, which is these two equations. So, after solving we can write the extensional actuation force F e as this, and F b the bending actuation force corresponding to the bending part is this. Now, the free strain in the top piezoelectric part is this, and the free strain at the bottom piezoelectric part is this. So, they just differ by this term T c top and T c bottom. Now, all we need to do is to find out the displacements, axial displacements at this junction, the top surface of the beam and the piezoelectric patch where they are meeting, and at the bottom junction the bottom part of the beam and the bottom piezoelectric patch where they are meeting. So, at the top surface of the beam the extension is delta L b top, which is this. So, this is extension due to the axial force F, and this is contraction due to the bending actuation F b, because we know that m divided by I multiplied by minus z is our stress here due to bending moment B, and if I divide that by E b, that gives me the strain here. And now, this m can be related to F b, and so F b becomes m b by T b by 2, or m b is F b multiplied by T b by 2, where m b is the actuation bending moment. So, this m b and m are basically same. So, if we write this in terms of F b and then put z is equal to T by 2, and after doing some mathematical manipulations this expression comes. The extension of the piezo can be written as this, we have been doing this, and if we equate these two expressions, we get this equation. After that we can do the same thing at the bottom piezoelectric patch and ensure that the extension at the bottom surface of the beam and the bottom piezo patch are same, and if we do that we get this expression. So, here we have used these terminologies ESE top, ESE bottom, they are just defined as this. ESE top is the axial stiffness of the top piezoelectric patch, which is BC TC top multiplied by EC. ESE bottom is equal to BC TC bottom multiplied by EC. The same expression can be rewritten in terms of this. So, we are introducing new variables alpha 1, alpha 2 and alpha 3, where alpha 1, alpha 2 and alpha 3 are this. Now, this equation can be solved and the expression for F top and F bottom can be found out, and this comes in terms of all the material and the geometric properties and the free strain at the top and bottom piezo. After solving these are the expressions that we get. Now, once we know the F top and F bottom and we know what is the actuation force, extensional actuation force in terms of top and bottom. So, we can write this, and similarly we know the actuation moment, we know the bending actuation force F b in terms of the F top and F bottom, and we can write this. So, here we have denoted this as M, we can call it M b also, since it is because of this F b. Now, this we get as the actuation moment. So, once we know these two quantities, or I mean these quantities, then we can solve for the deformation, stress, strain, and all of our quantities of interest. Next case is also an asymmetric actuation. Here the asymmetry is again in the piezo properties, but here the asymmetry is in piezoelectric material properties. So, D31 at the top and bottom are same. Now, the thickness is same. In the previous case we had thickness, a different thickness, but here we can keep the thickness same, or in fact we can have both the properties also different and we can solve it. So, again the similar thing happens here, even though there is same voltage applied at top and bottom, the forces can be different. So, we can write the same thing. Suppose the force here is F bottom and the force here is F top, and then again we decouple this into F E extensional part and a bending part, which is F b. So, we can follow the same approach, and again we can apply the compatibility condition here, that the elongation is same for the top surface of the beam and the top piezo, and also the bottom surface of the beam and the bottom piezo, and that will give us two equations. But in those equations, now since I have same material property for the piezoelectric patches, I mean the same geometric property, we get alpha 1 and alpha 3 to be same, and that is equal to 4 by E a b plus 1 by E a c 1. So, here E a c 1 means E a c of one of the piezo patches, and that is same for both, and then alpha 2 comes to be this. So, finally, the equation looks like this, alpha 1 and alpha 3 are same, that is the only difference between these two equations, and after that we solve the equations and we get our expression for F top and F bottom, and from there we can find out the actuation force, I mean the extensional part of the actuation, that is for that we get the actuation force, and for the bending part of the actuation we can get that force or the corresponding moment, and then we can analyze the same beam. Now, we look into the assumptions that we made in this, the major assumptions in this analysis. First of all, the shear in the bond is neglected. So, this piezoelectric patch, it is connected to the beam with a bond. So, there is a bond layer between the piezo patch and the adhesive that joins these two. So, if we look at it carefully, we will see that, I mean if we separate them and draw the diagrams, the shear diagrams, we would see that we can see the shear at the interfaces. So, this is how the shear would look. Now, the effect of the shear has been on this bond layer has been neglected. In fact, in all these analysis we did not consider the bond layer at all, because it is quite thin as compared to the piezo or the beam. Now, even if we consider the bond, our analysis technique will let us consider it for only its extensional and bending stiffness, but not for this shear effect. Next is the Euler-Bernoulli assumption that we made. So, it says that there is no shear deformation in the beam, that we neglected, and also while doing the blocked force method based analysis, we neglected the variation of normal strain along the thickness of the piezo actuator. So, in variation of normal strain along actuator thickness was neglected. So, as we saw that if I have a beam and if it has a piezo patch and if this bends, then in the bend shape it would look like this. So, there will be a variation of strain along the thickness of the piezo also, but that is neglected in the block force based analysis. So, these are the major assumptions that we made while doing this analysis. With that, I would like to conclude this lecture. Thank you.